Okay, so I'm really going to talk about work which is not even in progress, but which we hope will progress. And the reason I'm excited to talk about this is because this is what I think is a very creative endeavor by these three gentlemen, Siddhartha, Sugan, and Ritvik. And I think it's worth sharing with the audience, with friends, and to try and get some feedback about it. So there'll be few results. I'll just set up the context and try to explain what these three brave gentlemen are trying to achieve. Okay. And again, because it's a short talk, so for the purpose of the talk, the definition of turbulence will be that it's going to be solutions of Navier-Stokes equation or even experiments. We are not there yet, in the limit of very large Reynolds number. Sorry, the slide changer. Okay, so what's the starting point? So the starting point is this sort of, the notion of turbulence in terms of energy transfers, which was set up about a century ago, really a century ago in the 1920s. And these ideas go back to first Richardson, who was a meteorologist, and then sort of given more modern form through the work of Kolmogorov. And the whole idea is rather simple. It says that in a non-equilibrium stationary state, if you input energy epsilon at some large scale, for example, the scale at which the fan blades move, then this energy is transferred scale to scale in a completely space-filling way. And then at very small scales where viscosity starts to act, this energy gets dissipated. So on average, the energy injection is balanced by the energy dissipation. And this is sort of consistent if you go back and look at the equations of motion with the scalings invariance of the equations of motion. So one of the consequences of this sort of game is that turbulent flows should be self-similar, scale invariant, essentially non-intermittent, and we heard this word yesterday as well. And a great outcome of this is that if you are looking at correlation functions of velocity differences, and there's a sort of historical reason why people started looking at this object here, and then if you take higher order moments, then they all scale rather nicely dimensionally with an exponent p/3, which guarantees a certain Holder exponent h1/3. And just to sort of, map these two pictures, which might be useful for the later half of the talk, alpha is trivially related to 3h, and alpha, that sets alpha to be 1. However, if you assume this process, then what naturally follows is that when viscosity goes to 0, which is the really high Reynolds number limit, you end up with energy dissipation going to 0 because the fields are quite nicely behaved. However, when, post Kolmogorov, Richardson's ideas, when people started measuring these scaling exponents, they found that the Kolmogorov p/3, the simple dimensional form, is violated strongly. And here are some results from experiments. And there have been various sort of, work on this since the 80s, both in simulations and experiments. And more interestingly, perhaps, what you also find, and this is a bunch of data from various people, is that the energy dissipation rate actually converges to a finite non-zero value as the Reynolds goes to infinity. And that's what's known as dissipative anomaly. And this is one of the sort of important mathematical questions which exist in the field, is how does this come about? So real turbulence is intermittent. And so this rather nice picture of Kolmogorov, which assumes the flow to have a single Holder exponent 1/3, seems to break down when confronted with either numerical simulations or experiments for turbulence. So what's one way to fix this, and these go amongst models which are called intermittency or cascade models, is you can take the old picture that we have, but then using ideas from Mandelbrot, etc., then you kind of cast it in this form and say that as the energy gets transferred from scale to scale, the smaller scales are not necessarily space filling. So you end up with this whole process kind of converging on well, I'll use the word fractal in a bit, but end up converging on sets which have dimensions which are not necessarily the embedding dimension of the flow. And this sort of project was undertaken and given fruition. There were other heroes in the story in the famous sort of 80s work of Frisch-Parisi. And essentially what this Frisch-Parisi model, keep in mind that this model is not coming from the microscopics of Navier-Stokes. All right, so this is really a phenomenological model. And this kind of explains a little bit this departure of the scaling exponents from the standard Kolmogorov results. This model can also be used, for example, to explain that gradients of velocity acceleration statistics, all of them are intermittent and they depart strongly from dimensional arguments. So what's a good way to actually think about this cascade process and the fact that things converge? So one way to think about it using the same idea is to assume that the three-dimensional embedding dimension of the dissipation field allows now to have these fractal subsets with different scaling exponents alpha, and associated with each scaling alpha, let's say in a little band between alpha and alpha plus d alpha, you have a corresponding fractal dimension. So Kolmogorov, you have a unique alpha, you have a unique dimension, which is just d equal to 3, but now you're allowed to sort of play with this dimension. And just as a quick tutorial, one way to actually compute these exponents and the associated fractal dimensions. So this, for example, is a snapshot in one direction from Shiddatta and Sugan simulations of the dissipation field. So that's also an illustration of the fact that things are intermittent and not really stable. What you do is you can construct in a box of size r. So you construct little pieces of size r, and you can compute the total energy dissipation in those pieces. If the boxes are d-dimensional, here I've shown only for d equal to 1 for ease. And then you can write down an analogous sort of partition function from where you can fish out the something analogous to the Hausdorff dimension, or if you're doing information theory, this would be something very similar to the Renyi dimension. And then you can actually plot these quantities as a function of log r. And from there, you get this scaling. And from the scaling exponent, you can fish out the different fractal dimensions which exist in the flow. So this is an old program from the 90s, and which allows people to globally, and that's the important point, to globally construct what's known as the singularity spectrum. So for different values of alpha, you can fish out what f of alpha or the corresponding dimension is. All right? Not surprisingly, in a 1D cut, this is sort of peaked at 1, because that's your embedding dimension, and that's where most of the activity happens. So this is an old problem, and people have looked at this for some time. So the question is, what's the context? Why are we, again, kind of revisiting this problem today? So the context is recent results in the past few years, and I'll just go through them and we can discuss some of them over coffee, is the fact that there are now results, especially for weak distributional solutions of the Euler equations, which seem to suggest that we should look at the distribution of H and see in a field where those singularities are. So it's really like someone going into a jungle and trying to find exactly the points where singularities exist. And then there are recent sort of mathematical criterion which suggests that you do get, and this was on Sagar's conjecture, that in a spatial sense, if this room is my turbulent flow, there could be hotspots which have Hölder exponents which are less than 1/3. And that's the sort of feeling that has emerged in the last years, mainly work by analysts and PDE people. And so what Sugan, Shiddatta, and Ritwik set out to do is to take the multifractal picture. and for me, this is exciting because the multifractal picture, implicit in it is the fact that you need to move from H to Hölder exponents, which are functions of space, the fractal dimensions, which are functions of space, etc., etc. So if this is one region of the flow and this is another region of the flow, is there a way for me to localize information here and try to understand in this zoo in the flow, could there be regions which are singular and how long do they persist? And that might be a way to fix this idea of dissipative anomaly. So what was done was the following. Excuse me. So this is a two-dimensional cut of a dissipation field. And you meet 2 minutes. And you immediately see that there are regions which have strong dissipation and there are regions which are very quiet and without much dissipation. So, so what was done was now to divide these dissipation fields in little boxes. So you put on a grid like that and locally construct the singularity measures in each of these boxes. So you're blind to the fact that the flow is much larger than those little boxes, but you go ahead and actually look at the F alpha alpha, the DQ locally, and you can extract these values, all right? And so what we think for the moment, for lack of a better measure, that a crude measure or the roughness of the flow would be, for example, if I look at the standard deviation of these alpha of X fields. So I'm nearly done, huh? So here's the last couple of plots just to emphasize the working of this. So you see, I mean, if it's possible on this on the screen, you see that there is a near perfect correlation between regions which are monofractal, Kolmogorov-like, which are in this sort of greenish bluish color, and to regions where there are no singular events in terms of extreme value statistics. This can be modified even further, and what one can look at is the value of alpha. I mean, you can think about this as H1/3, where the F alpha distribution is sharply peaked. So there is no fractality in most parts of the flow, and those parts of the flow from the point of view of anomalous dissipation are the ones where things are very quiet. So let me end with this. So if you want to look at the full three-dimensional flow, so on the top, this is the dissipation field. The left side corresponds to regions which are, so I've imposed, or Siddhartha has imposed the color map of how fat the F alpha distribution is. And you see that they are really monofractal everywhere there are voids. And whenever there is extreme events of dissipation, you end up with things which are largely multifractal. So I'll leave with the conclusions and what we are about to do. As you see, this is outlook and hope in trying to exploit these tools to actually answer questions about identifying possible singular hotspots with H less than 1/3. Okay, I'll stop there.
Thank you, Samriddhi, for your wonderful talk. Questions?
When you subdivide the region into the small boxes, like because there's a numerical simulation, how many grid points do you have to take, or
so to get the Renyi dimension, for example, so if you have data information on, let's say, n cube points, right? So that dissipation field was probably for 4096 cube or 2048 cube, I do not remember. Then in each, so this is really coarse graining. So I want to look at things as a function of X, but I really cannot calculate it at one point because of the way you can calculate the spectrum. So we coarse grained around 8 or 10 eta, which is the smallest length scale in the flow. And that seems to be enough to actually give me the scaling from where I can fish out the respective fractal dimensions in the full geometry of the flow. And this, we've checked with different numerical simulations to see that it actually converges and the prescription works. Yeah.
is a good measure, right? What if you actually take the F alpha, extract the multifractal exponents, tau q's or whatever you want to call them, and look at the standard deviation of the tau q over the entire sample? Then you just get one number.
Then you get one number. So
And-
operationally, we actually do the opposite. One can first get the tau q from the partition function, which gives me q minus, and from there, something analogous to Lejeune transform sort of
Absolutely.
gives me an alpha F alpha.
So,
Yeah.
So wouldn't that number just be enough to tell you, or how that scales with, say, the overall?
Yeah. So for example, from the tau q, I mean, we didn't show this, but you could actually consider, let's say, the dq, especially for q0, q1, etc. Those dimensions have some meaning.
Yes.
For higher q, I have absolutely no feeling for what those numbers mean, right? So we are able also in these little grids to actually calculate the different d0s, d1s. I think that's what you have in mind, and then to look at that spread. However, just, this is my own bias, so I shouldn't, thrust it on Siddhartha, Sugan, and Ritnik. So for me, somehow I feel that the degree of departure from Kolmogorov or H1/3 fixed point is best captured in how wide the distribution of exponents is. But, I mean, I'm not completely sold to the idea, but that's just, yeah. If there's time, there's.
Hi. Is there any correlation between these regions of high multifractality with strain and vortical regions?
So the correlation that we have is an absolute correlation, absolute in a visual sense, largely, between the regions of high multifractality with the regions where you have anomalously large dissipation. So where you are breaking from Kolmogorov in terms of epsilon, right? Because as you know, the epsilon field in a given at a given time is also entirely intermittent. So whether those strong departures spatially are linked to the fact that you might have Hölder exponents which are less than 1/3, which allows you enough roughness. I mean, essentially, you can't integrate by parts if you have H less than 1/3. So even in the vanishing viscosity limit, it allows you to have finite dissipation. So that correlation is there. But you can take the next jump and try to understand the correlation between epsilon and strain vorticity fields. And so it can be a one-to-one kind of correlation.
So I have one question. The Hölder exponent, if it is less than 1/3, then there is supposed to be like inertial dissipation, right? Viscosity is not necessary to.
Exactly.
But then the structure is going to be very irregular. Then how do you expect the numerics to be? I mean, I'm just asking.
Sure.
How numerics has to be conducted.
So numerically, even for the spectral calculations by Kaneda and his group a few years ago, they were able to actually get the dissipative anomaly. In the sense, of course, you're always working with finite Reynolds number, in the sense that it did seem to asymptote already at Reynolds number, which were large but finite. That's one part of the story. The other part of the story has to do with in the last few years, work by Buckmaster, Drivas, etc. They're sort of applied mathematicians who were able to construct weak Euler solutions, so which are dissipative. They're not strong solutions, but weak solutions which are dissipative. And the conjecture is that for some classes of these weak solutions, you do pick up H less than 1/3, exactly what you were saying. So what we are after is to try and see whether in the Navier-Stokes for finite but large Reynolds number, whether these H1/3, how do they proliferate? Is the flow really singular everywhere, or do you need only some regions of singular behavior, which is good enough to kind of keep everything in check? So that's the
Samriddhi, I have a question. Hello, hi.
Yeah, hi, Sven.
How is it possible for the Euler equations to have a dissipative solution at all?
Good question. So if you take the Euler equation, So I'll answer in two parts, and then I'll move to something even simpler, which is the burgers, if that's okay, Sveta. So in the case of the Euler equation, if you want to construct a strong solution and you want to check energy conservation, all you need to do is, multiply the equation with U, integrate, etc. So the nonlinear term actually integrates to 0, and as you correctly suspect, the strong solution will conserve energy, right? However,
yes.
for this integration of by parts, you need to assume certain smoothness of the velocity field, right? So
Yes.
in the space of C1 alpha, right? C1 alpha is good enough, or
Yes.
in any Gevrey class that you can think of, this alpha has to be bounded strictly by greater than 1/3. This was actually a beautiful insight by Onsage in the 1940s. It's a beautiful paper. So what people in the last few years have seen is in these weak solutions, they are able to construct, they're able to bound the minimum Holder exponent to something which is very close to 1/3, which is the Kolmogorov limit. So just to finish the story, if you think about the zero viscosity one-dimensional Burger's equation, right?
Yes.
So there again, you can play the same game. There's no viscosity, so you would assume that energy is conserved, right?
Yes.
However, there is a finite time blow up because of which there's a shock. So at the shock, the velocity field loses its smoothness, which allows you to again do these integrations by parts and show conservation of energy, right?
Yes.
So the real Burgers, and in this language, there's a weak solution of the Burgers equation. Once the shock forms, you will always have energy dissipation, even though viscosity is exactly 0. That's because the tools that you're going to use for C1 alpha, when alpha is, not optimal.
Yes, I understand.
Did I answer your question, Spencer?
Yes, yes, that's very, very interesting. Thank you very much. Yeah.
So let's thank Samriddhi for his wonderful talk.
Thanks.